Section 1.2 is a catalog of essential functions. So we'll just review the different types of functions that we're going to see in the course commonly. In the last section, we talked about domain and range of a function, the definition of a function, and how to test whether or not a given relation in its graph is a function with the vertical line test. So this is just an extension of looking more specifically at which types of functions we might come across. So first and foremost, a mathematical model is a mathematical description, often by means of a function or an equation which might imply a function as its solution of some quantifiable real-world phenomenon. So list some examples of quantifiable phenomena without their associated equations or formulas. So maybe what I'll just write here is a few equations that might come to mind here. So velocity is equal to displacement over time. Force is equal to mass times acceleration. Physical laws such as this. There are lots of these in physics classes and even chemistry classes that we could come up with. And we won't generally be so concerned with what these things are and how they are applied in actual scientific applications, but mathematically, these are rather interesting functions. These are actually a little simple, but there are lots of different types of functions that are very useful in the sciences. And we'll be dealing with those types of functions throughout this course. So moving on, one of the most important functions we're ever going to deal with is a linear function. And we can think of a linear function as a linear model. So if two variables are related, maybe if f of x is a variable y, some output y, then it could be related to the variable x through the equation mx plus b. So we all know this y equals mx plus b equation to be the equation of a line. And now we're just extending this to think of it as a linear model. So we're thinking of x representing some actual real world quantity and its output in this mx plus b function being some other real world quantity. And we'll see an example of that below. So this is usually an oversimplification in actual mathematical models for real world items, but sometimes it can be close enough, right? And in calculus, we're going to use linear models or linear equations a lot to describe in close range or in small proximity more complicated functions. And we're going to find that describing things in terms of a linear function is actually pretty useful, and we can get a lot done with that. So a linear model for a phenomenon is one which represents the phenomena as a linear function, right? As we said. These are often too simple. I just want to emphasize that once again. So in other words, they don't capture all the complexity of a situation, but sometimes they'll capture the average behavior. So in the example below, we read that some scientists believe that the average surface temperature of the Earth has been rising steadily. They've modeled the temperature by the linear function capital T for temperature equals 0.02 little t plus 8.50, where capital T is temperature in Celsius and lowercase t represents years since 1900. So first question about this is, what does the slope of this equation represent? And then what does the t-intercept of this equation represent? Well, remember that this is where we're filling in m and b, the slope and the y-intercept, or in this case, the capital T-intercept. Okay, well, 0.02 times t, that looks like it represents a rate, right? Because we're going to plug in a time t, number of years past 1900, and we're going to get to we're going to multiply that by 0.02. So 0.02 must be Celsius or degrees Celsius per year. And right, our slope of 0.02, it means that capital T, the temperature, increases by 0.02 degrees Celsius each year, right? So if t, little t was equal to 1, we'd multiply that 0.02 times 1, and we'd be adding 0.02 to 8.5, and the temperature would increase by 0.02 for 1 year. So that's literally the rate of temperature increase per year, degrees per year. What is the t-intercept? Well, t-intercept is the value of the temperature whenever little t, or the time past 1900, is 0. So it's the temperature in the year 1900 in this model. So you see that 8.5 degrees Celsius was the average global temperature in the year 1900. So down at the bottom, it says use the equation to predict the average global surface temperature in 2100. And we'll see that when we plug this in, we're going to end up with 12.5 degrees Celsius. Remember, this is temperature as a function of 200 years after 1900, right? How did we come up with that? Well, remember that 2100. How many years after 1900 is 2100? Well, you take the difference, 2100 minus 1900, and you get this 200 years later value. Now, t of 200, we plug in everywhere there's a lowercase t, we put in 200. So matching that, and then simplify the arithmetic that ensues. We have, again, 12.5 degrees. They ask us to do the same for the year 100. That's scratched out, presumably because I didn't want to do that in a previous meeting. But you could actually do this exercise and realize that we're going to end up with something negative, right? We did 100 minus 1900 as we did before. And if negative 1800 is the year, and negative 1800, if we plug that into the formula, T, the temperature, negative 1800 years, so 1800 years before the year 1900, we're going to have 0.02 times negative 1800 plus 8.5. And what we'd ask ourselves when we're done with this is whether or not this value makes sense. Sure, it's accurate regarding the mathematical model, but is it actually useful, right? So I think this will come out to negative 36 plus 8.5, and that's going to bring us down to negative 27.5 degrees Celsius would have been the average temperature in the year 100. Now the question is, do we believe that that was the case? Well, we probably don't have measurements. They probably didn't have, well, they certainly didn't have degrees Celsius in the year 100 AD. So we don't have any record of what the temperature was in Celsius. I guess maybe there's some scientific methods to infer roughly what that global temperature might have been. But it'd probably be harder to prove that it could not have been this temperature. That's probably awfully cold. Remember that 0 degrees Celsius is the freezing point of water. So negative 27.5 degrees as the average global temperature would mean that probably a whole lot of the earth was frozen. So what we're seeing is not, we didn't do our mathematics incorrectly. Maybe this number is off by a bit. Maybe I didn't do that correctly in my head, but this is off from reality. We're just seeing a shortcoming in the model, right? So this linear model does not capture all the complexity of the situation. So that's the point I'm trying to make this other value. However, in the short term, in close proximity, like I was saying before, just 200 years into the future, the year 2100 after 1900, this model might be roughly correct. 12.5 degrees Celsius. You might need to convert that to Fahrenheit to see whether or not that seems like a reasonable temperature. Remember, it's well above freezing here, so or at least the freezing point of water, so it's probably a more likely scenario. So moving on, let's talk about the next type of function that we'll come across quite often, and sort of these are kind of going in order of friendliness, right? Our favorite function to see is a linear model typically. After that, it's an easy function to deal with that's a little more complicated than a linear function is a polynomial. So you'll remember from an algebra class that a polynomial is an expression of the form or a function of the form given here, where a sub n minus 1 down to a0 are all real numbers. So they could be whole numbers, they might be decimals or fractions, but they're the coefficients of the polynomial. And the degrees or the powers of x's here, well, n is a whole number. N is a positive integer. So, and that's required for this to be a polynomial. N is a rational number like 1/2, a non-integer, 2/3 or negative 1/3 in the power there, it would make it not a polynomial anymore, and we have a more complicated function on our hands. So if n is a positive integer, then that means n minus 1 is a positive integer, and so on down the line. We have x to the first power, x to the 0 power here, and we'd be dealing with, and we're dealing with a polynomial. So n, the largest power of x, again, when this is an integer, is the degree of the polynomial. and each of these elements along the way are called terms of the polynomial, or terms of the expression in general. So provide the algebraic representation and sketch the graph of each of the following. The identity function, well, remember this is one of our favorite functions, f of x. You give the computer x, it just gives you back x. It essentially identifies it. You give it 2, it gives you back 2, right? So we can think of a computer or a function as if, some sort of computer program where you input a value and it does a job and outputs a value. In this case, it doesn't do much work, it just outputs the number you give it. Similarly, f of x equals x squared. Well, in this case, it outputs, you give it the number x, then it squares the number and it outputs that value. So if you gave it a 2, it would output a 4. If you gave it a -3, it would give you a 9. So f of x, the cubic function, is, well, it just multiplies x by itself 3 times. These are all examples of power functions, but they're also polynomials, right? They're polynomials because each of their coefficients, they have one term each. Each one has a coefficient of 1, and each term has an integer, positive integer power of x. Okay. Generally, a power function can have any power of x, but for polynomials, for these to be single-term polynomials, this needs to be a positive integer, and in all 3 cases, it is. Notice that the first one has an understood power of x to the first or x to the 1. So those are our basic polynomial functions. Of course, we can add all these together and get, a more general polynomial. So we might write the function g of x as x plus x squared plus x cubed. And notice we could, maybe we could give it some new coefficients. This could be 2x plus 1/2 x squared plus pi x cubed. Still a polynomial because our powers are still positive integers, right? And our coefficients are real numbers. 2 is a real number, 1/2 is a real number, and pi is a real number, even though in order they're an integer, a rational number, and an irrational number. So polynomials, of course. We're going to find the polynomials are some of the easier functions to do calculus with after linear functions. So we mentioned a power function in the last page, and again, just to give this a general form, this is where we just have a single x to a power of a. So again, each of those functions on the previous page were all power functions. A is any constant, so this is any real number. In this case, like I said earlier, so now f of x equals x to the 1/2 is a power function, and they ask us to graph this power function. So we do so down below. We just recognize the f of x equals x to the 1/2 as the square root of x. Remember that these two notations are interchangeable. If that was x to the 1/3, we would say the cubed root of x, so on for any other integer underneath 1 in this power. Now we just recognize the graph of this and we can draw it immediately, or we might think it through and plot some points and remind ourselves what this thing looks like. So perhaps I did this. This is 1 on the x-axis, and the square root of 1, or x to the 1/2 power, is also 1. And then I might come out here eventually and find 4 on the x-axis. And maybe this isn't drawn very well, but somewhere around here we find, that this was a 2. This is certainly not drawn very well, but we get the idea, right? The other way to think about it is that y equals x to the 1/2 it corresponds to the equation, the inverse equation, x equals y squared, or y greater than 0, right? So we only get the positive version of the sideways parabola, x equals y squared. Right? So those are 2 different ways of thinking about it, but really just recognizing this as a basic function is fine. So other power functions look like the following: x to the -7, right? We're allowed to have a negative power in there, so it doesn't have to be a positive integer anymore. X to the pi even, right? X to some irrational number as a power is okay. Natural log of 2, Remember, that is a constant. You can plug that into a calculator, you get some decimal number. It's also an irrational number. X to that irrational number is a power function. X cubed, a more simple power function. This one actually counts as a polynomial as well. And then lastly, x to the arctangent of natural log of 3. Sure, you could plug 3 into natural log and then take that output and plug it into arctangent, and that decimal number can be x's exponent, and this is also a power function. So maybe this one was having a little bit too much fun. So power functions. Let's move on to the next function that we'll deal with quite a bit in this course. Those are rational functions. Okay, and then trigonometric functions follow that. So a rational function is a ratio of two polynomial functions. So in other words, it can be written in the form p of x over q of x. So where p of x is a polynomial and q of x is also a polynomial. So rational functions are famous for having somewhat limited domains, right? We have to remove points from their domains, or we have to remove points from the real numbers in order to express their domain. Because with q of x in the denominator, this polynomial might be equal to 0 at times, and we're not allowed to divide by 0, right? Or division by 0 is undefined. All right, so those values where q of x, those x values where q is equal to 0, must be removed from the domain of this function. It's important to know the domain of a function because we're going to do lots of operations on these functions where we might apply it to a set of numbers, and we want to make sure that we don't apply it to numbers that it's not defined for. The range maybe isn't as necessary, but still good to know. And this at times it'll come up and we'll need to know the range of one of these functions, and remember that this is all the values that the function attains, whereas the domain is all the values that the function that can be plugged into the function. So we note already that this is a rational function. Just to confirm, the numerator x is a polynomial, the denominator x squared minus 4 is a polynomial. So this is in fact a rational function. It's good to confirm even when it's claimed by the example. So what's the domain? Well, the domain is everywhere that this polynomial on the bottom, x squared minus 4, is not 0. So it's all reals except for x values where x squared minus 4 equals 0. So we solve for this equation, solve for x in this equation, and we get x squared equals 4, which is x equals plus or minus 2. Remember, we took the square root of both sides of the equation, so we need to put a plus or minus. We introduce the square root, so we put plus or minus. If we're just given a square root as a definition of something, there's no need to put plus or minus. So we need to exclude these 2 points. Notice that plus or minus 2, if I plug them in here, I'll get positive 4 for x squared, and 4 minus 4 is 0 in both cases. So those are the numbers that we're not allowed to have in the domain of f. So to write that in interval notation, remember you go from negative infinity to negative 2, excluding 2, and you have to union that together, sort of stick it together with negative 2 to 2, excluding both endpoints negative 2 and 2, and then we union that with 2 to infinity, again excluding 2, and we always exclude infinity and negative infinity. So there's our domain. Now the range, what's the range of this function? It's all the values that this thing attains. So, well, that one I'll leave as an exercise, right? I don't have it filled out here, but what you might think about is if I plug in negative values of x, it looks like I'll probably have negatives here, right? If I plug in positive values of x, I'll probably have positive values output. And that's not entirely inaccurate, but we have to think about what goes on the bottom, right? So remember that the way that you've done these in the past is that you set up a table, whether these are positive, when x is less than a certain number, x is more than a number. What you need to check is what is the range on each of these intervals, right, on their own. So maybe you set up a table to do that with these 3 intervals down the columns forming 3 rows, and then you put x and x squared minus 4 along the columns on the top, and then you just check to see whether or not it's positive or negative and whether or not x goes on to infinity or negative infinity. Another way to come up with one of these ranges is to look at a graph of this function, and you can see whether or not it covers all real numbers and what it might exclude. Just looking at this thing right away, I'm fairly certain that it is the range is all real numbers for your answer, but I'll let you check that on your own. Again, remember the domain is typically more important than the range with a lot of our applications. So lastly is a trig function, right? We've seen lots of trig functions in our second pre-calc class or our trig class, which is the class immediately before coming into this one. Those aren't going to go away. About probably 1/3 of calculus is done on trigonometric functions, so you really want to make sure you're solid here. Remember that there's sine of x, cosine of x, and tangent x. So the domain of sine, this is written out in its full name, sine with an E, right? We could have just as well wrote sine of x to get the point across. Well, this is negative infinity to positive infinity, and that's actually all real numbers, right? We can plug any number we like into sine of x. There's no problem with its definition. So it's well defined for all real numbers. This little symbol here, this R with 2 vertical bars in it, is the set of real numbers, right? So we'll use that quite a bit in the course. The domain of cosine is just like sine. It's another waveform. It's been shifted, right, to the right by pi over 2, or the left by pi over 2. I believe it's to the left. And its domain is also all real numbers. That shift doesn't change anything. So what's the range of sine and cosine? Well, remember that without any number in front of them, the amplitude goes from positive 1 down to -1. So -1 to 1, inclusive, because we attain those values, is the range of sine as well as the range of cosine. So tangent's a little bit more complicated if you happen to remember this. The domain of tangent is all reals, but except where it has a denominator of 0, right? Remember, tangent is equal to sine divided by cosine. So anywhere cosine is 0, which happens to be any odd multiple of pi over 2, so pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, negative pi over 2, negative 3 pi over 2, so on and so forth. There are infinitely many of those. So all those odd numbers are captured by the formula 2k plus 1. Then you take any integer you like, say 2, and plug that into this. And you have 2 times 2 is 4 plus 1 is 5. 5 pi over 2 is the result. And that's one of the places where cosine is 0. Sine of or tangent of x is sine x over cosine x. So anywhere cosine is 0, we have a point where the function is undefined. Now that's a point where it has a denominator of 0, so those form vertical asymptotes. Here's one at pi over 2, here's one at 3 pi over 2, and those go on infinitely. Note that to get pi over 2 out of this, we plug in k equals 0, and we have 1 times pi over 2, and that's this point. We plug in k equals -1, we have -2 plus 1 is -1 times pi over 2, so negative pi over 2, and we get negative pi over 2 here. So that's the domain of tangent. It's all reals except for, so this is really just written out in words. I didn't do a great job. We probably should have used set notation for this one, because or set builder notation. But that's an exercise for the student to do. But this captures the idea right here. It's basically just a word description of it. Remember, set notation is set of all values x such that x is not equal to, and then we do the 2k plus 1, pi over 2, and so on, where k is an integer. Right? That would be our set builder notation. I'll let just the student fill in the rest of that. What's the the range of tangent? Well, we just have to remember what the graph looks like. I think that's the easiest way to get to it. And below here, I've sketched a graph of tangent of x. And remember that each of these sort of offsetting curves reach downward infinitely and upward infinitely, and there are no holes or breaks in the middle of this function. So it turns out that this is the set of all real numbers, negative infinity to infinity. And note that in every one of its cycles, tangent actually attains all real numbers. So tangent's an interesting function, as well as its counterpart, arctangent, or the inverse tangent, which you've learned in a previous class. And we'll see that later on in the course, how useful arctangent is. So those are rational functions and trigonometric functions. Remember, for trigonometric functions, there are also the arc functions, the inverse functions, and there's also secant, cosecant, and cotangent, which have similar. They're all similar to tangent, actually. And that's an exercise to go through and remember the domains and ranges of those functions and what their graphs look like. So going a little further with things, remember, we're going to want to graph functions quite a bit because it's helpful to do so when we're trying to evaluate them. So if we're asked to graph a function like absolute value of x minus 3 plus 2, we just have to remember what transformations are taking place and that we need to look at the basic function or the parent function of this, which is actually the absolute value of x. So I'll sketch that one in. The absolute value of x we just looked at in the previous section. And it looks something like this. I dotted it in. This is y equals the absolute value of x. Remember that y and f of x are somewhat interchangeable. We just think of the outputs as values along the y-axis and the inputs as values along the x-axis. So remember, absolute value of 1 is 1, and that's how we get a point right there. So that's more or less what's happening. The absolute value of negative 2 is positive 2, and that's how we get this point right here. So again, rehashing absolute value as a graph. So let's see. X minus 3, this is a shift right. And then plus 2, this is a shift up. So both of these are just shifts. If we had a multiplier like a 2 in here, that would increase our steepness, right? Or 1/2 would decrease our steepness of these curves. With a 2, it would bring them in closer to vertical, and with a 1/2, it would bring them down closer to horizontal. Again, we don't have to do that. So I'm going to do both of these shifts in one go. I'm going to focus on this point here at the origin, the vertex of the absolute value graph. We're going to shift right by 3. In the last section, I talked about doing that as the where's the new 0 of this function for absolute value of x minus 3. So that's one way to think about it. Or we just recognize it quite literally as a shift, right? Just straight from the rules of algebra. And then shift up by 2. So this point's going to move up by 2. It moved over by 3, and then the vertex shifts up by 2. And the vertex will be right here at 3, 2. And if we think about it, if we put in 3 for x, we're going to get 0 plus 2, and we're going to have a point 2 here. So that more or less decides our, oops, I don't need to dot this one. Decides the graph of our shifted function, right? This is y equals absolute value of x minus 3 plus 2. So remember, transformations were done both in college algebra and trigonometry, right? You shifted trigonometric functions just as you shifted algebraic functions. So adding something within the parent function or the basic function shifts side to side, and then adding something outside shifts up or down. And just remember that we shift right for x minus something, we shift up for plus something, right? Adding a positive number. Okay, so that's transformation of functions. One of the last things we'll see quite commonly is the composition of functions, right? And this will be the last topic we talk about in these notes and video. So if we're given two functions, f of x equals the sine of x, g of x equals x squared minus 3, right? One's a trig function, one's a polynomial. Why is that a polynomial? Confirm that for a moment. They ask us to find the composition f of g of x. Right? Remember how to compose functions? We plug one function into the argument of the other. It also asks us to determine the domain and range of f of g. Okay, this new composition function. So f of g of x, we just have to remember what that means. F of g of x is really literally as it sounds. One way I like to write this, so a little intermediate step here would be to say f of g of x. So what I do is I pick up g of x as a function and I put it into f's argument. Remember that this space in the parentheses here is f's argument. So g of x is x squared minus 3. So here I am writing it in the argument of f. And that's just to, interpret what this composition notation is telling me to do. And then what I do from here is I say, okay, well, I've got this function plugged into f's argument. Now I apply f to the function. What does f do to its argument? Well, f takes an x and it takes the sine of that x. So this is our new x right here, x squared minus 3, and it takes the sine of that x, right? Now that x is a bit more complicated than just x, it's x squared minus 3. So anyway, our composition is sine of the other function. And it all just fits into f's argument. So what's the domain of this function? Well, the domain of sine is all real numbers. No problem plugging in anything to sine. Now, what's the domain of x squared minus 3? It's a polynomial. I might not have mentioned this before, but polynomials have no problems in their domain. There's no way to divide by 0, and there's no way to take an even root of a negative number. So polynomials also have domain all real numbers. So I can plug anything into this, and whatever number comes out of that is fine to go into sine as a function, or as an argument of the function. And this tells me that all the domain of this composition is all real numbers, negative infinity to infinity. What's the range of this function? Well, remember, it doesn't matter what comes out of this function. We're plugging it into sine. Sine never gives us a value that is more or less than -1 or more than +1. So its range is -1 to 1. Okay. Now, going the other way, find g of f of x. This is the second part of this example. Composing these two, that's the easy part, right? We just take g of whatever f of x is. Well, f of x is sine of x. So we're going to do g of the sine of x. So everywhere there's an x in my expression for g, remember it's x squared minus 3, I'm going to replace that x with a sine of x. Right, so now I have sine of x standing in place of x squared minus 3. Okay, so we write sine of x squared as sine squared x. We've seen this before. Minus 3. So there's our composition now. Okay, what's the domain of this function? Well, we can plug anything we like into sine of x, and squaring it doesn't change that fact. So sine squared of x has domain all real numbers. Minus 3 doesn't change any of that either. That's just a linear function. Linear functions also have, an x minus 3 or something minus 3. That's a x minus 3 is a linear function, is the way I'm thinking about it. These being the outputs of that's confusing. Let me back up on that one again. Sine squared of x has no problem with anything we plug into it, and then subtracting 3 doesn't cause any problems either. No division by 0 and no even roots of negative numbers. We'll leave it at that. So the domain of g of f is all reals. What's the range? This one's a little trickier. Remember that sine of x gives us numbers between -1 and 1. But if we square it, we have all positive outputs from sine of x now, right? It's squared. If we square -1, we get 1. If we square 1, we get 1. If we square 0, we get 0. So the smallest sine squared of x can be is 0, and the largest it can be is 1. It attains both values, so this is closed. And now what do we do with that range? Well, we're going to subtract 3 from values that come out of sine squared of x, which have a max of 0 or min of 0 and a max of 1. So then we're going to know that we range between -3, 0 minus 3, and 1 minus 3 is -2. So the range is actually -3 to -2. Now, if you graph this function on a graphing calculator, you'd see that that is holding up, right? And that's not proof, but that's just further evidence that you've, just a check to make sure that you've actually done this probably correctly. So that's it. That's our review of essential functions, and we did do 2 extra pieces, 2 extra skills, which is graphing functions with transformations and analyzing composition of functions. So that'll close up section 1.2.